Today we have a topic that is pretty advanced, I'll warn you. The topic is intermodulation, or sometimes called intermodulation distortion. In this video, we're going to talk about what really happens when you try to pull signals out of the air and run them through amplifiers, and what kind of trouble can you get into and how can you get out of it. And because this is an advanced course, we are going to do some math today. But before we do get into that mathematics, let's do a little bit of review. This represents our antenna, and this represents a radio. So there's some circuit boards in it, there's some integrated circuits, there's lots of other stuff, but I'm just abstracting it here. And in Radio Design 101, we learned how to make that work. In 401, we're trying to make it work as good as we possibly can. And that means we have to make it work with all the junk that's coming into our antenna. Now, there's a signal that we want, and that's represented here, and it's at a power P sub S, P sub signal. And we can do that, but as it gets weaker and weaker, it becomes more difficult, as we've talked about. And the reasons that it becomes more difficult are because of all this other stuff coming into the antenna. There is background thermal noise coming in. And we talked about this in, I think, episode 2. So you can look this equation up there and what it means and so forth. There is also radio frequency interference, which was the subject of episode 3, and that can be very substantial depending on what kind of buildings you're in or around. In episode 1, we actually talked about interferes, but we're coming back to that today. There's tons of FM radio stations out there for building an FM broadcast receiver. If it's Wi-Fi, there's tons of Wi-Fi access points that may be getting into your antenna. And they're all coming in and competing with the signal you want. Now in Radio Design 101, we designed and built an FM broadcast band receiver. So we're using that as a case in this video as well as some of the others. But that doesn't mean this material is focused on FM broadcast. It's just being used as an example. So here is our antenna. It's outside the university laboratory, and it's picking up signals from the local area as well as some distant points. And here is the spectrum that we see if we look at it on a very decent spectrum analyzer. This is a commercial quality, moderate cost spectrum analyzer, a little bit better than the tiny SA Ultra that you saw on the first slide. Let's see what we have here. This is sweeping from 87 megahertz to 109. So it's the entire FM broadcast band plus a little bit on each end. And each one of these spikes, of course, is a radio station, we hope. We're going to see in this video that signals like that one might be in question. Anyway, we can see lots of stations here, but there are many others that we cannot see. And one of the reasons is this spectrum analyzer has a noise floor of minus 100 dBm. And in episode 2, we quantified that, and we discussed things like what is the minimum discernible signal that you can get in a certain bandwidth. This spectrum analyzer is set to a resolution bandwidth of 30 kilohertz. And we should be able to see signals much weaker than this. The minimum discernible signal of this spectrum analyzer with the 30 kilohertz resolution bandwidth should be about minus 129-ish dBm. And what are all these dots? Well, these are the signals that you saw in that spectrum. They're just plotted as dots here. Now, we don't see any dots down here because, well, we had that noise floor of about a minus 100. Now, FM broadcast signals have a 200 kilohertz bandwidth, so they're not going to be this weak, so we don't care about that too much. But we would like to see signals down to at least minus 108 dBm, which is the theoretical sensitivity for an FM receiver, with a 3 dB noise figure and a decent signal-to-noise ratio at IF that would give us about 20 dB of audio signal-to-noise, which is a very usable amount. It's not great, but it's very usable. But we're not seeing signals down that low, and in fact, when we build low-power portable FM receivers, they often don't get signals below minus 75 or so. It depends on how many signals there are in the area. But we're missing all of the stuff with those receivers, And we're missing all the stuff down here that should be visible with the spectrum analyzer. We're missing that. And why are we missing all of these things with a commercial moderate cost spectrum analyzer? Okay, that's what we're going to be talking about. Well, one reason is noise, not the noise that's coming into the antenna from the environment, but noise generated in the circuits in the spectrum analyzer, or generally speaking, a receiver itself. But that's what these lines are talking about. We should be able to get signals down to minus 129 dBm on this spectrum analyzer display. Part of the reason is that we don't have the LNA or preamp on in this thing. We did try to turn it on, but it would not come on. It beeped at us horribly. So that's another thing we're going to talk about today, why that is. In fact, let's talk about that right now. I don't want to delay that too much. On this cover slide here, this is a tiny SA Ultra spectrum analyzer. You can buy these things for like $150. Now, this is going from 85 megahertz to 115. So it's, again, got the FM broadcast band plus some stuff on the left side and the right side. All these signals in the middle, or shall I say most of these signals here, are real. But what's all this stuff out here? Well, as we're going to see today, this is not real. Neither is that. Neither are many of these signals that the arrows are pointing to. These are called intermod products. Now, if you've seen episode 1 in this series, you know that those are the result of hitting the amplifier too hard. Remember the low noise amplifier or preamp that we wanted to try on, to turn on, and it just squeaked at us. It was saying, ouch, I can't do that. All right, so why? So in episode 1, we talked about compression, which is what this is about. I'm not going to go all the way through it again. And we talked about intermodulation distortion and intermod products. The problem is we've got one signal we want to get, which is very weak, minus 110 dBm right here. And then we've got other stations that are very strong. They're not super strong. I mean, they're shown at minus 40 dBm. That's not a strong station. But they're strong enough that when we amplify it by 30 dB, they become minus 10. Well, they're not in compression. But they have produced these other intermod products that were not there in the real spectrum coming from the antenna. So these are artificial. They're produced in the amplifier. And that's what intermod distortion is. Notice that this one is right here next to the desired signal, and it's stronger, so we can't get the desired signal. And that's what's happening with our tiny SA Ultra spectrum analyzer. Unlike the commercial unit, it doesn't squeak at you. It just says, okay, I'll turn on the low noise amplifier. Anyway, so here on the left is a spectrum I got in my driveway. This is our van, and I've got a dipole antenna. And then this little guy right here is the tiny SA spectrum analyzer. And here's the spectrum from 85 megahertz to 115 megahertz. The lowest signal I can see is minus 110 dBm. That's better than that commercial unit. That's interesting. But this is with the low noise amplifier in this tiny SA spectrum analyzer off. We're using a 30 kilohertz resolution bandwidth as we were in the other analyzer. But the noise figure in this thing is not quite as bad, but it's still bad. It's 20 dB. We should be able to get minus 129 dBm, and we're getting, what, minus 109 or something like that. So our analyzer noise figure is still 20 dB. So the solution is to put a low noise amplifier out in front, right? Turn on the LNA. This thing's got one inside. We're going to see it today. And here's what happened when I turned it on. The signal level for this really strong guy dropped from, what was it before? Minus 29 dBm to about minus 32 or minus 33 dBm. So it looks like that strong signal is being compressed. Now we're gonna examine that and see if it's true or not. That's why I put a question mark here. But what is very obvious happened is, look at all this stuff right here in this red circle. That's not over here. So that's not coming in. This is well above this noise floor, right? This is minus 90 dBm for the peaks on these guys. It should be showing up here, but they're not. And so they're not real. These are being generated in the low noise amp in the Tiny SA Ultra Spectrum Analyzer. That's true of this guy and some of these guys as well. And I'm trying to capture that here in this quote. Many signals seen below minus 75 dBm are now actually intermods. And remember, intermods, classically speaking, are when you've got like two strong signals and a really weak signal. So this is the picture that sort of reminds us of what's going on. Except here, there are a lot more than two signals, but any two signals can create a problem through that mechanism. It turns out any three signals, or any N signals can do that. And later today, we're going to talk about something that's not well known, not well discussed outside of the cable TV industry, where they have to deal with situations like this, where there are a crap load of signals all in the spectrum you're looking at. They talk about something called composite triple beat. And we will have one slide where I'll talk about that very briefly, but it's beyond this video. We're going to mostly focus on the so-called two-tone interferer problem that we see here, and that you see in all of the other videos and web pages that you look for this information in. And remember, this is Radio Design 401, so we're not as interested in talking about what intermods are and doing all the math. We're more interested in what can you do about them. Because if you're designing a radio, you want to make it as good as possible. So in today's material, in addition to the math that we will get into briefly and so forth, and talking about things like the multi-tone inputs, we are going to talk about solutions. And little spoiler alert, I'll tell you some of them. The most obvious one is don't turn on the low noise amplifier. So here's the spectrum with it off, here's with it on, and looks better with it off, right? We don't have all this crap. Another thing that a lot of radios do is give you an automatic gain control or an explicit attenuator that you can turn on. So here I turned on an attenuator. I put it outside the analyzer because you can't use the one inside it when you've got the LNA on. Anyway, I put the attenuator in and we get this spectrum, which got rid of the junk that we didn't want. But frankly, if you compare these two, they look about the same. So we might as well just have not turned on the LNA. But the better solution, if you have the ability to do it, is to burn more power in your receiver. So this is the so-called high power solution. And we'll come back to this slide, but basically, if you can afford to burn a watt in your receiver front end, you can probably avoid many of those intermods. And then in episode 1, we presented what I would call a white paper using something called a Q-enhanced front end, which is a very high Q, very narrow bandwidth filter out in front. Okay, now that we've seen some examples of what the problem is, let's talk about where it comes from, the real-world circuits, and the mathematics of it. What I'm going to do now is attempt to take us from this view, which is sort of a qualitative view of things, to what's really going on inside these amplifiers that produces these intermods. And that's what the mathematics is for. We need to characterize the output voltage versus input voltage of the amplifier. Ordinarily, you multiply the input by the gain and you get the output, right? But that's for a so-called linear amplifier. Now we're talking about non-linearities. Then we're going to talk very briefly about Maclaurin series, which is a special case of a Taylor series, if you remember any of your calculus or anything like that. If not, don't worry about it. We'll explain it. And then we'll look at what happens when the input is not a single sine wave, but is rather a two-tone input, so two sine waves together. So first, let's look at the nonlinearity issue. Here's some materials from episodes in Radio Design 101. The blackboard is actually from the class that Radio Design 101 was modeled around. And in this particular case, we have a common emitter amplifier. The emitter is AC grounded. The signal comes in over here on the base, and the output comes from the collector. And we go through all of the analysis of that in Radio Design 101 or in Intro Electronics courses. In the process of doing that, we have to understand what this transistor is doing. And so in a later episode of Radio Design 101, we looked at that. This is a transistor, and all you have to know here is that if you put a voltage between the base and the emitter, then if there's a voltage between the collector and the emitter, you get current flow. And as you change the voltage on the base relative to the emitter, it changes the current flow. And that's the basis of what's going on in this amplifier analysis. Vary the base emitter voltage, that varies the collector current. Oh wait, how does that create an output voltage? Well, we drag that through this pull-up resistor, and Ohm's law says that as the current changes, so will the voltage at this node right here. So that's how the output voltage is developed. For it to work well and linear, we need the collector current to vary linearly with respect to changes in the base emitter voltage. Does it? Well, no. In the Radio Design 101 analysis, we talked about this thing called transconductance, and it is a linearized version of what's really going on. This axis is the base emitter voltage. So as we increase the base emitter voltage from, say, this point to this point, then the current goes from this amount to this amount. And it looks like it's linearly changing. If we go half that distance, then it's going to go to here, which is roughly half as much change in current. Okay, so that's pretty nice. But if you swing over a wider range of voltages, then you can see that it's going to kind of taper off out here at the lower end, and this is an exponential, so it's going to go up very rapidly here, and it's not going to be linear. And I want to point out that this is not unique to bipolar junction transistors or this particular analysis technique. This is universal. It happens in vacuum tubes, in field effect transistors. It happens whether you use the transconductance model for the BJT or whether you use the older current gain model. It's still true that the thing will become nonlinear if the signals are too big. So, delaying the math a little bit more, let's look at some simulations. This is a common base amplifier that we designed in Radio Design 101, this section of it here, with a tuned LC load. On this one, I've actually added a common collector buffer so that the output impedance is about 50 ohms, or at least it can drive a low output impedance load. And in this graph are the input and output voltage waveforms. The input is this small guy, of course, it's 25 millivolts peak in amplitude, and the output is much bigger. And if you look at the numbers, you find out that the output is 10 times as big as the input, so the voltage gain is 10, which is 20 dB. And if our input is a 50 ohm source and our output is a 50 ohm load, then that's actually a 20 dB power gain. And as we can see, the waveforms look good. So at least eyeballing, I don't know, look at this. This looks a little soft down here, this looks a little peaky. But let's find out what happens when we increase the signal to 100 millivolts peak. Well, you can see what happens. The waveform is now distorted, which if you remember some Fourier theory, you would recognize that that means that there's probably some harmonics going on. But it's also, in a sense, smaller in amplitude. And here I estimated the gain now is 8 instead of 10, so it's 18 dB instead of 20 dB, and that's what we would call a 2 dB gain compression. The gain is now 2 dB less than it was before. It's compressed. And why is it distorted and compressed? Well, remember what we talked about here. As the base emitter voltage changes, the collector current should change linearly, but it doesn't if the signal is big enough. And we can see that in this waveform, which is the current waveform, the collector current waveform. It's got it very distorted and somewhat compressed down here. Okay, but that's not intermods. let's move on to a simulation where we have, instead of a single signal coming in of varying amplitude, we have two signals, actually a third signal here. Let me explain that. Here we're simulating the case of a very weak signal, microvolt level signal, in the presence of much stronger signals, 50 millivolts. In episode 1, where we went over this in detail, I explained why, even though this says 2 microvolts, this is 1 microvolt, and this is 50 here, and it's 25 here. That has to do with the loading that the amplifier places on this 50 ohm source. But let's just look at the 25 millivolt interferers, these two signals. They're at two different frequencies, 99 megahertz and 100 megahertz. So I ran a simulation for many, many cycles. That's why it's all solid looking here. And then I did a fast Fourier transform of these waveforms. And this is the output waveform, VO. And you can see there's the amplified input signal tones. And these are the intermod products. These are actually called third order intermod products for reasons that we'll explain very shortly. And these are fifth order and seventh order and so forth. But anyway, the output is nothing like the input. The input should be just those two frequencies. Notice also that you can't even see the amplified version of the desired 1 microvolt signal in this FFT. However, over here on the right, we can. What I've done is decrease the interferer levels by 20 dB. They were 25 millivolt, now they're 2.5 millivolt. I left the desired signal at 1 microvolt. I've also shifted the desired signal to 98.5 megahertz instead of 98 megahertz like it was before. And that's so that I can distinguish it from the intermod product, which was falling on that 98 megahertz. But notice what happened here. The output signal levels got weaker, of course, because the input got weaker. But the intermods have dropped a lot. In fact, they've dropped so much that the desired signal is now stronger than the intermods. And that's all because we attenuated the interferers by 20 dB. So they dropped. And in the math, we're going to see that they drop faster than the signals that are here. These dropped 60 dB when these dropped 20 dB. Okay, that's getting weird, and that's why this intermodulation stuff is somewhat difficult to wrap our heads around. But let's press on with the math. So here, finally, is that mathematics. I'm simplifying a little bit by going from that single transistor amplifier to what's called a differential amplifier. And you may know about these, you may not. If you don't worry about it. The point is that you have an amplifier. The output voltage change here is bigger than the input voltage change. And we can see that on this graph. If the slope of the output versus input voltage characteristic is greater than 1, then we have amplification. Here it looks like it's about a slope of 2. So for a 5 millivolt input, say the peak of the sine wave reaches 5 millivolts, the output is about this much, and that's about that much. And anyway, it's about 2. But the problem is that if we get too big, say bigger than 10 or 15 or 20 millivolts, the output gets compressed. And it's obvious in this graph that that would happen. How do we model that in mathematics? Well, if you know about Taylor series, then that's what we're doing. We're coming up with a polynomial expression for the output versus the input voltage. In this center region right here, where we have small input variations, the output should look like VO equals A1 times VI. That's just a linear gain. But in order to model the rest of this curve, we need these other terms. I'm calling this a Maclaurin series. That's a special case of a Taylor series where you expand about 0. It just makes the equations not as messy. But in order to model the rest of this curve, we need second order and third order terms in the expression for V out as a function of V in. Then, after we have this polynomial expression for V out versus V in, we use it to see what happens when the input is a sine wave. Is the output still a sine wave, or how distorted is it? That's what we're going to do with this. And we're going to start simple with the so-called single tone case, where the input is just a single frequency sinusoid. In episode 1, we saw how an interferer at a level of minus 10 dBm could get compressed and have an output of 0 dBm, and that's if this amplifier is running on low power. Remember, we were assuming it's a 5 milliwatt amplifier, so it can't put out more than about 1 milliwatt, and that would be 0 dBm. But how is that captured in the equations here? Well, we put in this for the input, put it into the first term, and we get A1 times V cosine omega naught t. That's straightforward. That's just an amplified version of the input. The output voltage is A1 times V, where V was the peak magnitude of the input sine wave. All right, so this is expected. It's the expected small signal output. What do these other terms do? Well, the second order term in the polynomial expression for V out versus V in produces this when this is the input. And what is this? Well, you can get from here to here with the squaring operation when you use trig identities. So I'm not going to review that. You can look it up. But the result is you get a constant term plus a cosine at twice the input frequency, which is the so-called second harmonic. And the DC aspect of it means that you have some rectification, or more simply, you have a little bit of DC offset in the output. We don't care about that because usually these amplifiers have some DC blocking capacitor, so that's not going to hurt us. This second harmonic probably isn't going to hurt us either, because after this amplifier there's some more filtering before we go to the mixer, and that'll be stripped away. But what happens with the third order term in the polynomial? So here we're going to take V cosine omega naught t and cube it. Well, cubing it is the same as squaring it and then multiplying by it again. So you can take this and multiply this and use your trig identities and get this. But notice the ellipses here. I didn't write out all the terms that you get. I only wrote out terms that I care about. So there are additional harmonics, etc., that are not shown here. But there is a third harmonic term shown. But look, there's also a fundamental frequency term shown. And that's added to this one. So this is the expected output for a small signal amplifier. But now, because of the cubic distortion term, we get another component at that frequency. And if A3 is a negative number in this Maclaurin series expansion, then this will subtract away from this if A1 is positive. And so that's what happens, and that's what gives us gain compression. Now, if you're like me, you don't like looking at big, messy math expressions. That's part of the reason I didn't throw in all the other terms here. What we'd rather look at is what matters in our design. And in that case, we might want a graph like this, where on this axis we have the input power, and on this axis we have the output power. And we know that they should be related by the gain. So at 0 dBm input power, we have, say, plus 10 dBm output power, which means we have a gain of 10. And then if we had 10 dBm input, we could have 20 dB output if our amplifier is burning enough power. But at some point, the output is not going to go up as the input continues to go up because it's not drawing enough power to generate that output signal. So we're going to see this compression curve. And when it deviates by 1 dB from what we hope or expect or want it to be, then we call that the compression point. And there's an input compression point and an output compression point. Usually in a data sheet, you'll see the output compression point spec because it's the bigger number, so it's better for marketing, right? But sometimes they'll show the input compression point as well, the input referred compression point. In any case, let's take the output compression point. I make a claim here that it's typically between 0.1 and 0.5 of DC power consumption. Actually, you'll almost never find it being half of the DC power consumption. So if you have something drawing 5 milliwatts, you'd be lucky to get out 1 milliwatt, not 2.5. 0.1 would mean that a 5 milliwatt powered amplifier would get out half a milliwatt. Or what is that in dBm? -3 dBm. But this is an incredibly important statement in design. The output compression point is very strongly constrained by the DC power consumption. And we'll see that again moving forward. The other statement here is that if you know the output compression point, then you can subtract off the gain and find the input compression point. There's always a question about plus or minus 1 there, but that's a detail I want to get into. Gains are usually 10 or 20 dB. Now, again, this is just the single tone case, not the two signals that form intermods. But this case and the 1 dB compression point are still very, very important. So as an example, remember this case where we had the spectrum analyzer without the LNA on, and then we turned it on. And if you look at the signal level here, it was -29 dBm, and here it's -32 dBm, so it looks like it's compressed. But I gotta warn you about something. When you're taking measurements like this, the resolution bandwidth here was set at 30 kilohertz. And this is FM broadcast. And FM broadcast signals are moving back and forth by as much as 75 kilohertz. So this amplitude will change over time. You'll see it bouncing up and down. This is a static captured picture, but it will move up and down. So it's quite possible that this wasn't actually -32 dBm, maybe just when this picture was taken. So that's why I said here, strong signal, now compressed, question mark? Well, let's find out, or at least attempt to find out. Let's look at what's inside this guy. This is going to be fun. I wanted to get information on the amplifier that's used in the Tiny SA Ultra Spectrum Analyzer. So I looked for what's called a teardown. And Kerry Wong has a nice teardown page here. And you can see the circuitry. And he actually identifies the chips here. This is the RF input connector. And signal comes in, there's a blocking cap, and then there's this. This is a electronic switch that routes the signal either through this path or through this path. The lower path has the attenuator. This is like 0 to 30 something dB attenuator chip. But if you want the LNA, then you have to switch to the upper path, and this is the low noise amplifier chip. And then it goes on either this route or this route into this, which is a low pass filter, and then it goes into a mixer that up converts it, in the case of the lower band 0 to 850 megahertz, up converts it to, I don't know what these filters are, probably 915 megahertz or something. They're soft filters that provide the very strong channel selectivity. But let's take a look at this chip. I pulled the datasheet for it and found this. The LNA has a gain of 24 dB at this frequency. It's pretty flat. But here's the thing. The output compression point is plus 5 dBm. So what would the input referred compression point be? It's not shown here in this abbreviated list of performance parameters, but you can use the equation. It's the output compression point minus the gain. So let's call this 5. Let's call this 25. So it would be about minus 20 dBm. So that doesn't sound like to me that this thing should be in compression. But compression is usually not the most serious problem. It's a way to get to the intermod problem, as we'll see, but it's not the most serious problem. The most serious problem is the intermod problem that produced all this junk and some extra signals in here that aren't real. So that's where we're going to go now. So we've made it through these first two bullets and halfway through the third bullet under the math. Now it's time to look at what happens when we feed two sine waves into that Taylor series expansion. That will then prepare us for talking about the intercept point third order, IP3, or the input referred intercept point third order, and the relationship of that to the 1 dB compression points. This is what most of the videos and web pages seem to concentrate on. And that's good, it's fine, but it's kind of limited because it's just for two-tone inputs. You got to start somewhere though, right? But in a dense spectrum environment, you really have a multi-tone input case. So we'll talk about that for about 30 seconds or so. This probably deserves an entire new video, and frankly, it deserves a whole lot more attention in the research area. We'll also touch on something called Spurious Free Dynamic Range, and how that allows you to assess the maximum signal level that you can have before you get this intermod problem, and how that is driven by the DC power consumption in your circuit design. And then finally, we'll go over those solutions that I previewed at the very beginning of the video. All right, so let's get back into the math for a little bit. This is going to be the two-tone input where you have two sine waves at different frequencies. Our actual concern deals with trying to get the weak signal when you have those two interferers, and they produce new intermod products that could block your ability to get that desired signal. So there's really three signals, but we're only going to focus on two, the big ones, because the other one is like 70 dB weaker, and if you were included in this math, you'd find out it doesn't really affect the result. Here, they're represented as an input signal, which is V cosine omega 1t plus V cosine omega 2t, where V is a constant, the peak amplitude of the cosine waves. I assume them to be the same strength because that's classically what you do in one of these analyses. And so I'm assuming that the power is minus 40 dBm. So that works out to be about 3 or 4 millivolts peak amplitude for the V here. And if you go back to our curve like this, we're getting toward the nonlinear region, but we can't visually see it. But this is typical of when intermods start to happen. They happen when it looks like you're still linear, but you're starting to get into the nonlinear region. And in this example, I showed the output being minus 10 dBm because we had a 30 dB amp. And I showed the intermod products at minus 70 at the output. Now, where those numbers come from? Well, that's what all this math is going to allow us to figure out. So what we do is really easy. Well, it's tedious, but easy. We stick this expression for Vn of t. I didn't write the dependence on t here, but it's implied by this expression. We put Vn to this expression here, and we crunch and crunch and crunch, and then start trying to pull out the stuff that matters. And I've seen some good web pages and videos on YouTube that actually walk you through all of that math. I'm less concerned about the math and more concerned about the engineering. So that means I'm interested in the first term because, well, that's the desired output, the expected output. So there it is. And then there's some squared stuff, and that creates offsets and harmonics, blah, blah, blah. But one of the terms that comes out of this, not all of them, one of the terms that comes out of all of this is this line right here. So in the expression for the output voltage waveform, we have some constant, which is going to depend on A3 and some of the trig identities that we needed to get to this point. But what we need to notice is the expression for the frequencies here. So there's 2 omega 1 minus omega 2. And there's 2 omega 2 minus omega 1. There's also a V cubed. So whatever amplitude the signals were here, it's going to be the cube of that for the amplitude of these terms. That's going to be really important. What about the frequencies here? Well, the first one is the intermod product that flanks on the left. And it's separated from the two signals that created it by the distance between those two signals. So that's what I'm trying to draw here. This term, 2 omega 2 minus omega 1, we take the frequency f2, or omega 2, and double it, and then subtract off f1, so we don't come back fully, we only come back to here, and that's what creates the right-hand term. But let's come back to the amplitude of these intermod terms. Remember, they change as v cubed as the input signal changes as v. So if the input signal doubles, then these things are going to go up by a factor of 8. Or conversely, if the input signal is dropped to 1/10 of the previous value, then these are going to go down to 1/1000th of the previous value. And that's why they can drop very rapidly and become non-issues. The real question is, at what point does that happen? And that's what these graphs that you may have seen before, if you've looked into this at all, that's what these come from. There's something called the third order intercept point. Now, we're going to get back to this, but before we do, let me show you some example real-world spectrums that I took in the lab. Here I'm looking at the output of an amplifier that we had in the laboratory. I had the amplifier hooked up to 2 input signals coming from 2 signal generators and a power combiner. So in the first spectrum after the amplifier, I see the 2 signals and pretty much noise everywhere here. But then I cranked up these guys by about 3 dB, and so at the output they went up by 3 dB. And oh wait, look, intermods, there they are poking up out of the noise floor. Then I increased the levels by 2 dB, so they went from here to here, and the output level went from this level to this level for the intermods. And that's about 6 dB. It almost looks like 5, but it's really 6. Remember, intermods initially increase by 3 dB for every 1 dB of the input signal increase. So here, I increase the input signal by 2 dB, so the intermods go up by 6. You can prove that to yourself by an experiment like this. If you do, however, be careful that the signal generators are not generating the intermods when you combine them together. You got to be careful in the laboratory environment in your setup. Anyway, let's go on higher than this level and see what happens. Oh, look. Looks to me like I went up by 10 dB, yep, plus 10. And what happened to the intermods? Well, they were down here, so should they go up by 30 dB? That would take us to, let's see, right here. Oh, that's where they went. But look, now there's some other guys. These are called 5th order intermod products. Those are from a 5th order term in the Taylor series or Maclaurin series expansion that we didn't do, but you get the idea. The important take-home from this is that the 3rd order products amplitude increase 3 times faster in dB than the 1st order product, the expected output. And so that's what this is saying here, and that's what it's saying here. So I warned us in the beginning that this material can get pretty heavy, and you're starting to see that. We've covered the expansion of the transfer characteristic of output versus input voltage, and we've looked at the production of these intermods. What we haven't done is come up with and then explain these really strange graphs. Now, some of you have seen them before, so I've got to walk a line here between people who haven't and have. Fortunately, you can freeze these videos and then go back to them. So maybe you want to take a break right now. I could make this a 2-part video, but I think I'm going to keep going. You can always pause it here and please come back. Okay, so now we're ready to talk about intercept point 3rd order, IP3. Now remember this set of graphs. As we increased the input signal level, the outputs went up and they tracked the input dB for dB. But at a certain point, intermods started to come out of the floor, and then they started to go up 3 times faster than the outputs. So when we increased the input by 2 dB, the intermods went up by 6, and so forth. Let's see what that means in an extrapolated situation. What it means is, oh look, here we went up by 10 dB and these guys went up by 30 dB. So maybe if we go up by another 10 dB, then they will equal or overtake the desired guys, or the expected guys. That's what this 3rd order intercept business is about, sometimes called intercept point 3rd order. The input power is on the horizontal axis, and the output power is on the vertical axis. Output power of what? Well, the signals that are generating our intermods, those are called P1, And if the input power is here, then the output power is higher by the gain, and it should just keep on going up. But we know that there's compression, so it's going to bend over at some point. But this is how the output tracks the power level of the inputs plus the gain. Now, the third order products, they start somewhere, but then they start going up really, really fast with a 3-to-1 slope. This is a 1-to-1 slope. And so, oh wait, they're going to stop going up too because, well, the amplifier just can't amplify outrageously, so they're going to stop going up. But if you take measurements down in the lower power regions and extrapolate, you get to a point called the intercept point, where the level of the third order intercept is equal to the level of the signals that produced those intermods. In data sheets, they will sometimes quote the third order intercept point. It's often quoted as the output intercept point because, well, it's the bigger number. But they sometimes quote it as the input intercept point as well. They might give you both of these numbers. These two numbers are only differ by the gain in dB. All right, so this is supposed to be about real world stuff, so let's bring in a data sheet. This is the data sheet from the low noise amp used in the Tiny SA Ultra. And I showed you these numbers before. This is in the tabular data, and sure enough, there's the IP3 at the output and the IP3 at the input. Sometimes this would be called IIP3. We can take either one. Let's take this output third order intercept point. They claim it's plus 18 dBm typically. Varies a little bit with frequency, but in the range that we care about, it's probably 18 dBm. Now, remember the gain was 24.5 dB, so we could get the intercept point at the input by subtracting 24.5 from this, and it'll give us about minus 6.5, which is minus 7. They're just quoting it at minus 7. So that's good. Let's look at the relationship between the intercept point at the output and the 1 dB compression point at the output. The IP3 output is 18. The 1 dB compression point at the output is plus 6 dBm. So what's the difference? 12 dB, right? Okay. But maybe that's just for this specific amplifier. How does it work in general? Well, I've looked at tons of amplifiers, and this is not a blanket statement, but I will say that in general, I found the intercept point to be 5 to 15 dB higher than the 1 dB compression point. So great, what do we do with this? How is it going to help us in our circuit and system design? Well, this is a busy graph. It's the one that I had on the cover slide. It's a very busy graph until you realize that it's pretty much the same as the intercept point graph with some additions here. The additions are that I put the noise floor on this graph. So here's the input referred noise floor, some negative 100, 120, whatever dBm. And here's the output noise floor, which is the same as the input noise floor plus the gain. So what we really want to have happen is we want the interfering signals, these would be the two-tone signals that are on this curve, we want them to be small enough in amplitude, say down here or so, that the third order products fall below the output noise floor. And in this graph, that point is labeled as PI3, input power third order. I don't know why I labeled it that. It's a dumb label. But the difference between that input power and the noise floor is called the Spurious Free Dynamic Range. And it's always less than what I call the 1 dB dynamic range, which is the difference between the 1 dB compression point. Remember, this is where it was 1 dB compressed. It's the difference between that and the noise floor. So now let's look at an example with some real numbers in it from some real amplifiers and figure out what all this stuff means. This is our problem. When the LNA is on in the Tiny SA Ultra, we generated all these intermods, and we don't want them. We'd like them to get below the noise floor. So how can we calculate what the maximum input signal level would be for that to happen? Well, the first thing we have to do is give up on looking at a real-world spectrum here. We have to fold back into the math world of you got two signals and they're the same amplitude. You can do it with two differing signal amplitudes. It gets trickier and it would make this video last way too long. You can even do it with more than two signals, like is here. This is the real-world case. But let's just say we have a two-tone case. So ignore the spectrum for a second and just imagine there's two signals maybe at this amplitude. How do we figure out if the intermod's going to be above the noise floor? Okay, tighten your seatbelt here. This is a work in progress. We're not considering the so-called composite triple beat, which is a partial solution to the problem of multi-tone input. And it also doesn't consider unequal values, as I said. We're just going to assume there's two values that are the same. All right, here we go. Consider the tiny SA spectrum analyzer with the LNA that we looked at the data sheet for. We know from the data sheet that the output 1 dB compression point is plus 6 dBm. However, if we didn't know that, if we just looked at the DC power consumption, which it turns out is about 60 milliwatts, then we can use this approximation if we're designing the thing from scratch and wanted to figure out what's going to happen. We could just say the output compression point is 60 milliwatts, the DC power consumption of the chip, times 0.1. That'll give us 6 milliwatts. That's 7.8 dB. That's pretty close to 6. All right, you can come at it either way. Read the data sheet, or if you don't have a data sheet and you're designing something, then you can come at it this way. Now, the input compression point is the output compression point minus the gain. That's easy. Using the 7.8 dBm value, that would be 7.8 minus 24, is about minus 16 dBm. So that would be this value right here on this fancy graph. Meanwhile, what is the input referred intercept point third order, the IIP3 value? Well, using our approximation, it's the input compression point plus 10 dB, or maybe 12 dB, whatever. I use 10. So if the input compression point is minus 16, I add 10, I get minus 6. Or if I got a data sheet, I'm not designing it myself, then I just look it up, it says minus 7. What's the input referred noise floor? Well, from episode number 2 in this series, it's this expression. And this is assuming we're using the 30 kilohertz resolution bandwidth, which is what I used in all the spectrum examples, including this one. But in that episode, it said plus noise figure. In episode 3, we talked about radio frequency interference and how that pretty much elevates your noise floor. So I just kind of put those in parentheses here. Figuring out exact value to use here is a little tricky, but let's just say we're operating outdoors, and so maybe it's about 9 dB, 9, 10 dB, whatever. Anyway, so this number here, the first two terms, we had previously said that that was minus 129 dBm, which you can calculate it. I add 9 to that to get minus 120 dBm. So that would be this value here. Now, if you're really, really good with geometry, you can probably come up with this expression for yourself from this geometric construction. But I just gave a reference here for where you can find it. It's a worthy formula to remember. The spurious free dynamic range is 2/3 of the difference between the input referred intercept point and the input referred minimum detectable signal. And using the numbers here, I got 76 dB. So that's this distance here. So PI3, the magic that we want to get, the input signal maximum level before we generate intermods, if we happen to have two signals at exactly the same level, would be the MDS plus spurious free dynamic range, comes out to minus 44 dBm. Whew! All right, now look at this spectrum. Well, we definitely got one signal bigger than minus 44 dBm. This is minus 20 at the top, 10 dB for division, so this signal is also above, and this signal is also above. This signal's below, but if it's weighted together with this one, the average is still above the minus 44. So a lot of these stronger signals here can be creating intermods. And in fact, even more can. Remember, this doesn't consider what the cable TV people call composite triple beat situations, where you are mixing 3 signals together, not just 2, to generate intermods. Here's a paper that I found online that talks about that. There's another IEEE article which is pretty good. Unfortunately, it seems to be behind a paywall, so I didn't put it up here. But what this paper talks about is if you've got a heavily loaded cable TV system, which is similar to a FM broadcast band where you've got tons of signals in the general area, then you could have many or even tens or hundreds of intermod products all land on the same frequency. As a matter of fact, here is a 27-channel system, and they had as many as, 230 signals all land on that frequency. So even though there's a bunch of guys here that are less than -44, with that taken into account and averaging this with the lower level signals and comparing that with -44. Anyway, you put all that together, and I think that explains these right here. Again, this is a work in progress. If you know about research going on in this area, please put it in the comment section. I think this is an area that really needs more work in today's world. It's really strange how some things like this that seem like people ought to know the answer to, they don't, because nobody's really looked at it except in the special case of the cable TV industry. So let's conclude our episode 4 with solutions. This is what you can do to address this problem in a real-world situation. One solution, which has been known for over 100 years, is apply an attenuator or cut it back on the RF gain, or both. So here there's an attenuator in this radio, and it's turned on by pressing and holding this while holding that button, whatever. And this was in our radio architecture's final epilogue of Radio Design 101, if you want to look at it. We also have this radio in some of our videos, and it has an AGC button that you can turn on and off, so that will help. And here's a demo that I did when I had a dipole antenna on the hood of my car outside, so it was away from most of the RFI. And I used the Tiny SA Ultra and looked at the spectrum with the LNA off, and this is what I got. And then I turned the LNA on, and I got, well, yeah, we talked about that. So here the LNA is turned on. In both cases, I've got 0 dB attenuation. Now, I can't turn the attenuator on inside this guy with the LNA on because of those 2 different signal paths that I showed you in the teardown picture. But what I can do is apply an external attenuator, and that's what I've got here. So the antenna has a cable that comes into this end. I punch in the 2 and 8 dB buttons, so I've got 10 dB attenuation through this guy, and then that goes into the spectrum analyzer. And here's what I get. It looks better, right? It doesn't have all the intermods out here or out here. It's better. But is it better than this? I'd say not really. So this is just a easy/partial solution. This is not the real solution. One real solution that we've mentioned a couple times in this video, as well as in episode 1, is to burn more power in your low noise amplifier and your mixer and everything before your final channel select filtering. So this is a ham radio ICOM 735 high frequency, that means 3 to 30 megahertz transceiver. And the LNA they use is this, and it burns about a ½ watt. And the mixer they use is similar. It burns a ½ watt. And then the final filter is here, and it is a 15 kilohertz crystal filter. Ordinarily, I'd want more than one, but it looks like they've got filtering here in this transformer and filtering here and filtering here. So that provides the extra out-of-band interference that you need when you're trying to make a radio receive 100+ dB dynamic range. But that's a lot of power. That's 1 watt. How much would it gain you? Well, you can go back through those formulas. Let's see, 1 watt versus 10 milliwatts. That's a factor of 100 in power. That's 20 dB. So it's going to change your input preferred intercept point up about 20 dB. It's a high cost, right? I mean, we're burning a watt to get up 20 dB. All right, well, it does work, and people use this, and car radios tend to be fairly good FM car radios as long as you're out away from RFI sources, and I'd be willing to bet they burn maybe not a watt, but several hundred milliwatts. But for portable stuff or energy harvesting radios, probably not the right solution. So we've been working on a solution for low power things like that, and we call it a Q-enhanced front end. It's been in episode 1 in detail, and so I'll refer you to that if you want to understand it and look at it in more detail. But what it allows you to do is filter and amplify the input spectrum, but select a signal, and the filter that we're using is about 200 kilohertz wide bandwidth. So it attenuates all of this other stuff a lot while it's amplifying the desired signal by 30 dB. So you can see the, I'll call it signal to interference ratio here, looks to be about 20 dB, whereas here it's 10, 20, 30, 40, 50, 60 dB. So that could be traded off against a whole lot of power burn. So that's why I think this is a worthy research area. Okay, that was an awful lot to go through, but hopefully it's been useful to you. You can always go back and look at it in more detail, and certainly sample some of the other videos on YouTube where people cover this kind of material. Thank you for watching, and hopefully we'll see you in the next video.